So, welcome back to our last series of seminars for this season here at BrIAS with our BrIAS fellows. Today we have a kind of slightly longer program than usual because we will have our usual seminars. Then we have a third seminar instead of usual two with a special guest. And we will also have the closing ceremony for this season of BrIAS with various people who will intervene. It is really my pleasure, and I'm very happy to introduce the next speakers. In particular, I have a very special debt of gratitude with the first two speakers because I've been some of the most important people in my career. I will start with the first, that is Professor Ilya Kolmanovsky from the University of Michigan. So he's a dear friend of our university. This is the third time that he stays here on a long stay. The first one was something like 8 years ago with a chair-in from ULB. And then 2 years ago, he was awarded the chair Jomot at the Royal Academy of Sciences, and we organized several events there. And now it's here as a BrIAS fellow. Now, Ilya is one of the most known researchers in our area. He has a long list of prizes, which I will not mention because it's really long. And I see that he's happy that I don't mention it. And he has a very peculiar career because after his PhD, rather than continuing in academia, went for a long time in the industry. So he was for almost 15 years in Ford Motor. While being in Ford Motor, he was keeping doing both applied and theoretical research of a very high level, and then he came back to the university where he continued this amazing career. So he is author of various hundreds of papers, author of more than 100 patents. I think you crossed the 100, Ilya. You crossed the 100 patents. And is really very well known in our society. Is also the editor-in-chief of the IEEE Transaction and Control System Technology. And most of all, is a very dear friend, and he has always a lot of very interesting things to say. So I'm very happy to give him the podium.
Thank you very much for a very kind introduction, and I'd like to thank BrIAS for for giving me the opportunity to spend time here in Brussels, interact with colleagues and Professor Garoni and other colleagues visiting BrIAS. Was really wonderful time and very productive time with a lot of good ideas and good exchanges. I'd like to say a few words about some of my research and some of the adventures in an area called model predictive control and computations. Before I do that, I just want to tell you a little bit about my broad area of research, and that involves control of systems with constraints. And in automatic control, you typically have a system, we call it plant, that you're trying to control, and then you have a controller. And then in the traditional control, what you'd like to do is to cause certain outputs of your system, here they're denoted by Z of t, to track certain references, which are denoted by R of t here. And what makes constrained control unique, or what distinguishes constrained control, is that you have additional requirements on this or other variables of the system that they have to belong to prescribed ranges given by the set capital Y. And examples of constraints include things like safety limits, obstacle avoidance requirements, comfort limits, actuator range and rate limits, as well as constraints can be more interesting. They can depend on time in case of moving obstacles, or can be given by temporal logic expressions. And why do we worry about constraints is because bad things can happen if constraints are violated. Cars, ships can roll over. The aircraft engine can catch fire because of compressor surge, battery can overheat, aircraft can disintegrate in flight due to excessive loads caused by maneuvers and gust, and actuator control surface rate limiting can induce pilot-induced oscillations that can cause aircraft crashes, and that's what we would like to avoid. If you take a flight, it's interesting that one of system with many constraints is the aircraft gas turbine engines. There is surge margin limits, overspeed over temperature limits, combustion limits of various kind, actuator range and rate limits. And as aircraft is becoming more electric, you have to also worry about constraints in electrical power system on currents, voltages, state of charge, and so on and so forth. One of the most appealing tools developed in control theory for addressing constraint control problems is what's called model predictive control. And in model predictive control, you generate control by solving a discrete time optimal control problem. So the feedback control law is obtained through the optimization. And the optimal control problem, the constrained optimal control problem, might look something like shown here on a slide. And here, let me make sure that I have a pointer. Here you have a cost function that you're trying to minimize that reflects your performance objectives. You have certain variable, you have state variables, you have a model, which is used as a constraint. And here, whenever we have a hat, that means the predicted state and predicted control. And then the way you enforce the constraints is by imposing those constraints as a part of this optimization problem formulation. And so the first element of this optimal control sequence that solves this optimization problem is assigned as your control action. So a couple of remarks here. Typically, you use iterative optimization solvers to find the solution. And so you have to solve this problem in real time, and that's why computations are important. And so the control law is not given by explicit expression like a PID law, but it's what we call algorithmically defined. You can obtain it after executing a particular algorithm. Often people refer to a diagram that I show here on the right that illustrates the prediction performed at time k. You predict the trajectory forward in time, you optimize this trajectory, you apply the first element of the optimal control sequence, and then what happens is that the real system doesn't behave like your model predicts. And so what do? Well, you repeat this process at the next time instant, and that generates a form of feedback to compensate for the uncertainty. Model predictive control has a long history. It emerged in late 60s in academia and in late 70s in industry, basically independently. Has been a vibrant discipline for academic research for several decades now. And it has been very successful in chemical process industry, and there has been increasing interest and adoption by other industries, notably automotive industry most recently. And I showed a few examples where it was actually introduced into mass production. Now, this is my introduction, and what do I want to do for this talk? First, I'd like to tell you a little bit about a few applications where we use model predictive control. Applications are always fun and gives you a little bit more idea about some of the applied research that I do. And then the Achilles heel of model predictive control is in the computations, because you have to solve an optimization problem on board, and that's difficult. And in fact, that's a major motivation for looking at alternative schemes, such as reference governors, this major area of research of Professor Garonia, as well as barrier functions and control barrier functions that have become popular recently. Hopefully, by the end of this talk, I'll convince you that there are a number of approaches to generate lightweight implementations of MPC that simplify the computations greatly. And so then you can take advantage of the fact that MPC is a very versatile framework that reflects performance objectives, handles constraints, and can have a low computation effort. If I have time at the end, and I'm not sure that I will tell you a little bit about how we can take ideas in computations and model predictive control and apply them more broadly to study the optimization algorithms in multidisciplinary design optimization. So there's more an area of design or area what's called control co-design, where you worry both about design and control together. So let me start talking about applications. And as I said, that in MPC, an optimal control problem has to be solved on board. And so the deployment of MPC still represents a very significant challenge, in particular in small aerial platforms like quadcopters, where onboard computing power is quite limiting. And here we are testing MPC controller for elliptical trajectory tracking in our M-Air facility at the University of Michigan. But MPC solutions based on onboard optimization we are able to realistically implement are limited due to the lack of computing power. Here is even a more significant challenge, both from computational control standpoint, which involves control of aircraft with high aspect ratio flexible wings. Such aircraft are of great interest as high aspect ratio wings increase lift to drag ratio, and therefore they can improve fuel or energy consumption. You can also use them as high altitude, long endurance platforms, basically pseudo satellites. Unfortunately, these aircraft are also very flexible, and they can experience high deflections and loads as they are exposed to maneuvers and wind gas disturbances. Furthermore, they have fairly complex dynamics, as you can see from these videos, and the models for them are high order, maybe between 100 and 1,000 states. And they also have numerous structural and control effector constraints throughout the aircraft structure that you have to worry about. So some of the work on the computations has really been motivated by looking at applications of this kind. MPC can also be used in spacecraft control applications, in particular for station keeping and rendezvous in proximity operations, notably on halo orbits in cislunar space between Earth and the Moon. And here, to enable low fuel consumption during station keeping, there needs to be special formulations of model predictive control used, and that requires accurate models, nonlinear models, and non-standard choice of cost functions. And of course, these non-standard problems, optimization problems, need to be solved reliably on board of the spacecraft. We have considering the use of MPC to handle constraints in deep space applications, for example, for soft landing on asteroids, satisfying various constraints. Then if one wants to improve the ability to fly around and land on an asteroid, essentially without much knowledge of the gravitational field, MPC and adaptive control can be integrated together. And I wanted to mention these developments because they happened under an AI planning grant from the National Science Foundation that Professor Bruno Sinopoli, who is the next speaker, has led. And this work was in collaboration with Professor Spen Zhao and Naira Havakimen. Here we integrated L1 adaptive control to compensate for gravitational field uncertainty and model predictive controls, as well as reference governors in other articles. Another application for which we successfully exploited MPC involved the reduction in emissions of diesel engines, and they are used to power trucks, ships, and interestingly, even some airplanes. And the controller architecture that evolved was actually quite interesting, and it involved not a single MPC controller, but actually 3 of them, and 2 of them were controlling the air pass of the engine, basically exhaust gas recirculation valve and variable geometry turbocharger. And the 3rd MPC controller was outer loop MPC controller that would adjust the set points to this inner loop MPC controllers, as well as the fueling rate. And while this architecture is quite complex, it enabled us to gain fairly good control over the engine transients, and we've been able to reduce transient oxides of nitrogen spikes, which is a difficult thing to do in diesel engines, and we've been able to do it with this architecture. And what's interesting also that thanks to some of the ideas on the computational side I'm going to talk about, we've been able to maintain the total computation time for all these 3 controllers under 1 millisecond per time step. There have been a number of applications we looked at to hybrid electric vehicles that exploited interesting ideas and interesting cost functions in optimization, including those based on game theory. Broader use of game theory We also considered that in applications to autonomous driving. And here what we worry about is interactions with human-driven vehicles, in particular in scenarios where an autonomous vehicle has to take into account these interactions. If the autonomous vehicle trying to merge into very dense traffic where there is a lot of other cars, it has to nudge its way in. And so you have to have predictive models that somehow going to account for reaction of human drivers. So game theory provides a way of modeling these interactions. And what we typically do is that we don't use a single game theoretic model, but use multiple of them. And based on the history of interactions, few seconds of interactions, we adjust the probability of each of these models being assigned to a particular vehicle. And then we use stochastic model predictive control to actually optimize the trajectory of our autonomous vehicle in such scenarios. More recent work, I'm not going to dwell on it too much, but that included taking into account perception uncertainty. If you have a camera-based system, you rely on a computer vision to drive in traffic. You have to account for uncertainty, for the errors in this perception system. That's a long-standing challenge. And also, perception systems are often based on neural networks. These are typically machine learning based systems. And the other challenge is that you have to take into account let's see if I can click. I don't think the video is playing. That's OK. You have to keep into account what's known as out-of-distribution perception, meaning that you might encounter during regular driving situations which were not present when you trained your perception system. And so we use deep ensemble type techniques to handle out-of-distribution perception. And if this video was playing, you could see that we are basically testing in environment with rain and bad weather, a system that has been trained in sunny weather. And this is in carless simulation. Now, there was a very nice conference here last week on the batteries. And we've been also looking at battery control problems more from a higher level systems perspective and on aspects that involve thermal management. And thermal dynamics in vehicles tend to be slow. The temperatures don't change very fast. And what it means is that if you want to prevent the exceedance of limit on the temperature, on the battery temperature, and you can have control over cooling system, you have to pre-cool sufficiently far in advance to avoid this constraint violation. So sufficiently far in advance of some kind of load increase or acceleration of the vehicle. So you need long prediction horizon. You need to look long into the future. And there are two issues there. One is that MPC has high computational cost. And the second is that the forecast uncertainty. You need to know what the vehicle speed and what loads are going to be able to predict the thermal loads on the vehicle. And you need to predict, say, the vehicle speed, let's just say 5 to 10 minutes ahead to be successful. Initially, we were skeptical whether we can do this long-term prediction of vehicle speed, but it turns out, and this is based on historical data, that if you combine queuing models for short-term prediction and then neural network and Bayesian network models for longer-term predictions, you can make some good progress on this problem. And then you can develop special variants of model predictive control, what we call a multi-horizon MPC, where you have different phases, and you have a receding horizon phase and a shrinking horizon phase. And a shrinking horizon phase, you can use lower fidelity model, you can use less accurate preview, and that helps reduce the computational cost. And we've done work developing this multi-horizon MPC formulation. All right, now I gave you a few ideas about applications. Computation in all of them is a serious limiting factor in terms of the type of solutions we can deploy. We have to worry about the computations. And so the need to address this Achilles heel of MPC has motivated us to look more systematically into computations and model predictive control. And I'd like to tell you a little bit about some of the research that we've done in this area that broadly categorized in 3 different directions here, 2.1, 2.2, 2.3. And our first set of approaches was to look at developing solvers, computational solvers, specifically tailored for problems, for MPC problems. And they would be faster. They would exploit special features of these problems, take advantage perhaps of warm start. And this is the work that involves many different ideas. It's the work with many collaborators. I could probably give a number of talks on these ideas. I'll just briefly mention 2 of these developments. And one of them is what we call inexact Newton-Kantorovich method for model predictive control. And this goes all the way to the classical Newton's method for solving nonlinear algebraic equations. So I have a smooth equation, f of x is equal to 0, and I want to solve it. How do I do it using Newton's method? Well, you take a guess for the solution, which is x0. You linearize your nonlinear equation, and you solve the resulting linear equation, and that gives you another guess, x1. You repeat this process, and you converge to the root, right? That's classical idea of Newton's method. Now, it turns out there is a Kantorovich version of the Newton's method where you don't relinearize. You just keep iterating with the slope computed at the initial point, or it could even be some approximate slope. It doesn't even have to be computed at the initial point, but the slope stays the same, so you don't have to regenerate the linearization. And furthermore, you could even don't need to solve the linear equations to completion. You could solve the system of linear equations up to some accuracy, and you still get convergent iterations. Now, in a setting of model predictive control, these ideas are quite appealing because often you have a pretty good idea what the solution might be from the previous time step if you use the warm starting. You already computed your solution one step ago, so now you are recomputing it for the changed state, but the state didn't change a lot. So you have a pretty good idea about what the solution would be if you use warm starting. And so few chip iterations of this kind would be very appealing because you could improve the solution just enough to give you a good control performance and satisfy constraints. Now, there is a challenge, is that in model predictive control, it's a constraint optimization problem. So you don't have a smooth nonlinear equation. You have Karush-Kuntaka conditions for optimality or Lagrange multiplier rule from calculus that you have to satisfy. And it turns out that that is what's known as variational inequality. And one of the things that we have done was to extend these ideas of inexact Newton-Kantorovich method to the case of variational inequalities, derive convergence guarantees as well as the estimate of the region of attraction. And indeed, if you apply this Kantorovich ideas in model predictive control, you could integrate them into sequential quadratic programming or into non-smooth Newton's method as well. You see a nice reduction in terms of the average runtime and maximum runtime. And in this particular case, we use it for spacecraft attitude control with the control constraints. Now, the other development that I wanted to mention along this first line of research is a joint work with Professor Bruno Sinopoli, who is the next speaker. And here we look at continuous time primal dual flow algorithms. And a nice feature of them is that they guarantee the feasibility with respect to constraints. So you have always constrained admissible solutions, irrespective for when these algorithms are interrupted or terminated. So if you are in a situation where your time to compute the solution varies, you'd like to have an algorithm that's anytime feasible. You can stop it at any time, and the solution that you have satisfies the constraints. And then adding a few bells and whistles to this idea, you could also ensure that this solution can be stabilizing and ensure closed loop stability as well. Okay, now let me talk about the second line of attack at computations in model predictive control. And that's where we said that suppose we are not able to solve our optimization problem to completion. Perhaps we are only able to perform a fixed number of iterations per time step. What happens? Could it be that maybe one iteration per time step is good enough and gives us good quality of the solution. Let's say that we are looking at a situation where we have fixed number of iterations per time step, and we also use warm starting from previous time step. And then our view of model predictive control changes. So ideal optimal MPC, we typically think about it as a static control law. So we take the state and we generate the control action. Now, if we do suboptimal MPC, we use fixed number of solver iterations per time step and warm starting, this control law becomes dynamic. So my optimizer becomes a dynamic controller that runs in parallel to my system. So the state changes. I perform L iterations of my optimizer for this updated state. I spit out the control, and the state of the controller is the guess for my solution, for example, for my optimal control sequence. And then the properties of this interconnection are going to be dependent of how many iterations per time step I'm able to perform. And so here's an example of an inverted pendulum on a cart, where with optimal MPC, where that is this problem solved to completion, I'm able to balance the stick. This is a pendulum on a moving cart. I can also do this job with 15 iterations per time step, but if I drop the number of iterations to 5 per time step, my closed loop system becomes unstable. I'm not able to stabilize it. Now, of course, this is a toy example, but these issues become important when you, say, try to land a SpaceX rocket that has somewhat similar dynamics. Now, it's possible to analyze this situation using a tool from control theory, which is called small gain theorem. And the basic trick is to rearrange the closed diagram as an interconnection of an ideal closed loop system based on model predictive control and the optimizer error subsystem. And the optimizer error subsystem has an input as a change in a state, and its output is the inexactness of the solution. So it's a disturbance by which your control action is performed. So it's an interconnection of these two systems. The other key step is to note that by increasing the number of iterations L that the solver can perform, the input-output gain, the asymptotic gain of this optimizer error subsystem, under reasonable assumptions can be made arbitrarily small. So then you want the product of two gains to be less than 1, and so you can find how many iterations you need for the closed loop system to be asymptotically stable at the origin and locally input to stay stable. You can also develop procedures to estimate this L star for certain types of problems, in particular linear quadratic MPC. The computations are quite tractable, as well as constrained regions of attraction. And we've been exploiting these procedures in a practical problem, including for spacecraft pointing with reactionable desaturation, stabilization of vehicle dynamics, and others. I should point out that the value of this bounds, L star, and the number of iterations that you need, these analytical bounds, they can be conservative. In other words, in practice, you actually need less iterations to get a stable closed loop. But the value of them is that you can examine the trends, and you can figure out how to modify your optimization problem and how modify your MPC problem formulation to reduce the number of required iterations. For example, if you increase the horizon of your MPC problem, you have more decision variables, and it's not surprising that L star typically increases. Now, suppose you want to lower L star, what could you do? Well, one of the things you can do, you can increase the weighting on your control in your cost function, make control more expensive, and L star is going to actually decrease. So there's some interesting conclusions that you can get. Yes, please.
Would it be a problem if you had to estimate the state?
That's a good question. I think you can definitely analyze the situation. We haven't done that.
Just an error in
right. Right. Yeah. So we do have LISS guarantee for that system, but we haven't. I don't think we have made it specific to the state estimate necessarily. Now, here's a third idea, or third approach from which we looked at the issue of computations and model predictive control, which is to say that suppose we are interested to solve our optimization problem to completion, but when is our solver really needs a large number of iterations? When is L needs to be large? Well, if your system is running in steady state and you're using warm starting, then nothing changes, right? The solution that you computed one step before is pretty good, and maybe you can improve it a bit by using one iteration per time step so that you have extra feedback. You don't lose the feedback, but that's pretty good. So if you look at where the spikes in the number of iterations occur, that typically happens when the problem data change. How can the problem data change? Well, the reference command, the command that you want to track, R, that you give to the system, that command can change, right? The pilot or the driver could give you a different command, and you have to track it. And indeed, you see the step in this pink dashed line, and this is where the number of iterations spike. So how to deal it? Well, how to deal with this? Well, you simply don't want to apply the step in a command. Maybe you apply a smaller step and then give it a ramp, and if you arrange things in the right way, perhaps you could run the system with just one iteration per time step. So this is an idea which is closely related to reference governors, and this is what we called a computational governor. And the idea of computational governor is to minimally alter the reference command to enable MPC optimization problem to be solved cheaply, efficiently, and reliably to completion. So I take my original reference RK, I pass it through the computational governor, it alters it to VK if needed, so that this model predictive controller solver can find the solution very, very efficiently. That's the basic idea. Okay, so how can we design this computational governor? I'll show you one development with some technical details, so you could see how this can be set up. I'm going to look at a special class of model predictive controllers called linear quadratic MPC. So it's the cost is what you have in linear quadratic optimal control. It's linear model quadratic cost function on state and control variables. And in such a case, the optimization problem you have to deal with is a quadratic program. So here you had is the control sequence that you're trying to solve for. And this, the constraints of this problem become linear inequality constraints. And theta is a parameter. It's a parameterized QP. And parameter consists of your state xk and from your reference, which has been changed, v sub k. So that's the setting. Now, how do you solve an optimization problem like this? Well, you use Karush-Kuntakas conditions, which is Lagrange multiplier rule. And this is a stationarity condition, basically that the gradient of Lagrangian is set to 0. S is a slack variable by which you relax the constraints, B lumps L theta plus little l. And then lambda are Lagrange multipliers that have to be non-negative. You remember slacks have to be non-negative. And then there is a complementary slackness condition, which is SI lambda I has to be equal to 0. But in numerics, we typically set it equal to small number, and we decrease this number when we address these problems numerically. So this small number is eta, and we have to decide on it as well. Okay, now we don't like this KKT conditions because it's a system of both equations and inequalities. I don't know how to apply Newton's method to inequalities. So what you do is that you do logarithmic transformation. You define lambda is square root of eta e to the power gamma. Gamma is a log space variable. That's my new decision variable. And S is going to be square root of eta e to the power minus gamma. And so the product of them is going to be exactly eta, and they're both going to be non-negative. So that kills all of my inequalities. I just have equalities left. And to equality, these are my equations. And I can apply Newton's method that we just looked at before. So this is how the Newton step D would look like to adjust gamma. So gamma is a decision variable, D is a Newton step. And to determine Newton step, you need to solve the system of equations, linear equations. All right. Now, this is what's called logarithmic domain interior point method, or LDIPM. Now, what about this computational governor? Well, computational governor has a form of traditional reference governor. It's a linear interpolation between previous value of computational governor output and current value of the command. And the interpolating factor is kappa. That's something that we are going to choose. And we are interested in setting kappa as close as possible to 1, so this computational governor doesn't modify the reference when it doesn't have to do it. Now, the question becomes how to pick this kappa. And it turns out that in this case, you have to pick kappa together with this eta, the homotopy parameter, by solving a linear program. It's a 2-dimensional linear program, so it's easy to solve. There are very special fast solvers for that. What you do is that you want to maximize kappa, you want to minimize eta, you want to bring eta to 0 as much as possible. So this is the cost that you're trying to minimize. Kappa is in between 0 and 1. Eta is within a chosen range. And the key constraint that you need to satisfy is that the Newton step D here in infinity norm has to be less than or equal than 1. So this is a Newton step of first iteration, and this gamma k tilde is a worm-started log space variable. So this is something that we determine from the previous iteration. There is a particular worm starting procedure that's being used. So it turns out that the Newton step D can be expressed as a linear function, or its infinity norm as a linear function of parameters. So indeed, this is a linear program. Now, why is it we want to do this? We want to maintain infinity norm of D to be less than 1. Because then nice things happen. You can show that then all subsequent LDIPM iterates are in fast convergence region and guaranteed to be primal dual feasible. So it has actually its similar property to robust early termination algorithm I talked about, except that this is now in iteration domain, not in continuous time. And then the feasibility, what does it mean primal dual feasible? Well, it means that feasibility is maintained even if you have state and terminal constraints. And horizon here, you could actually work with short horizon MPC that's okay too. So state and control constraints will be strictly enforced. So the idea is that the computational governor basically bounds the suboptimality of warm start by enforcing this constraint. And through additional analysis, you can show that nice properties, nice convergence properties that are usual in reference governor theory also hold for our computational governor. What do we see in terms of computations? We're able to reduce the computations by an order of magnitude in examples that we look at. We can also run with short horizon MPC and additional state constraints. The region of attraction is expanded. That's not surprising. That usually happens with the reference governor. But for conventional MPC, the region of attraction is backward reachable set of your terminal region, and that depends on your reference R. And when you use computational governor, your closed loop region of attraction becomes a union of regions of attractions for different values of the reference. That's a nice result, but it's not surprising. Some experiments in a lab here we are running this inverted pendulum in a cart. There are two screens. This shows the modified reference command and original reference command, as well as a true reference command. And then on the other screen, we are showing number of optimized iterations, and it's always equal to 1. So we are running with 1 iteration per time step, and you can imagine that in this case, computations are very, very simple, and we're able to satisfy constraints and do everything we want. Now, some of these ideas have actually been implemented in production with Toyota. This is a press release that if you'd like to read. So it's nice to have also some real-world impact. And to mention some of the additional and further work along these lines, we looked at this logarithmic domain interior point method, which is a nice way of solving quadratic programs. And we further developed it. One thing that we observed is that inside LDIPM, you have to solve linear system of equations that I showed, right? Well, do you really need an exact solution of that? Could you live with inexact solution? And we typically solve it using conjugate gradients. Well, you don't need an exact solution. And so if you set up inexact conjugate gradients, and this is always theoretical guarantees that we have, but in a range of examples that we've done in this paper, we have a reduction between 20 to 70% in terms of the computation time. So this is what we call inexact log domain interior point methods. And then I should point out that this idea of supplementing MPC an MPC solver by some kind of supervisory scheme that keeps it happy, it seems like it's very appealing, and we've been looking at a number of other ideas along this line, in particular something we call iteration governor that not only modifies the reference command, but it also chooses the number of iterations a solver needs. We have a stability governor that enables the use of short horizon MPC without terminal constraints and with large region of attraction. Some versions of model predictive control use a preview, and we have a feasibility governor for preview-based MPC that facilitates implementation of such MPC with short prediction horizon as well as large region of attraction. And then something that we haven't converged on a name yet, even though we published already a couple of papers. I call it incremental reference governor, even though within our group we haven't uniformly agreed on a name. But the idea here is that we are able to set up model predictive control based on low fidelity model, and the reference governor then uses a high fidelity model to protect the solution against constraint violation. So we can basically, and we can do other things that combine this idea of designing schemes on low and doing optimization low fidelity models, but then making sure constraints are enforced on high fidelity models. I did want to do time check, Professor Garoni. How much time do I have?
How much as you want?
Okay, so I'll then continue according to my plan. Let me just show you just very briefly stability governor. That's a scheme that is also kind of interesting. And what is the issue here? So asymptotic stability under MPC feedback is often guaranteed through the choice of the terminal penalty and terminal set constraint. So if you want to rigorously guarantee closed loop stability, what you typically do is that you constrain your end state at the end of your prediction horizon to a terminal region, and you also have to use a terminal penalty. Now, that's okay, except that in practice, this terminal constraint, which is shown in red box, is not something that practitioners like very much. One is that it's difficult to compute it offline. It complicates the online optimization because it can be quite complex, add some additional inequality constraints to your problem, which could actually be nonlinear in principle. And also its use can degrade closed loop performance because a lot of the control energy goes to satisfy that constraint. So people don't like it. Now, if you remove it, then it weakens associated closed loop stability guarantees. And in fact, it also weakens properties as well. So you could, your region of attraction can decrease. So what can we do in this situation? So let's look at this closely. Well, let's just drop this constraint, terminal constraint, and see what happens. So I'm going to look at terminally unconstrained LQMPC. And here I have the same problem that I had in the previous slide, but now here I drop the terminal constraint. The other thing I've done is that I replaced R, my reference, by V, because I'm anticipating that I'm going to use a reference governor-like scheme, and I will make this V different from R. Now, what happens for this terminally unconstrained MPC? Well, if you look at the case of linear quadratic MPC, so quadratic cost functions linear model, then it turns out that you can show that there is a region of attraction for this terminally unconstrained MPC, and it's given by a sub-level. This region of attraction can be computed as a sub-level set of your optimal value function. It's not surprising that sub-level sets of optimal value functions are regions of attractions. That commonly happens in MPC, and it happens in this problem. And the size of that set depends on parameter alpha, and alpha is what we call size of implicit terminal set that you can define. There are a lot of details here that are not important, but the important part is that this guaranteed region of attraction is typically much smaller than the region of attraction that results from a terminally constrained MPC law. So we lose something. We have a guarantee of, if we start sufficiently close, that will be stable, but it's a bit of a problem. So what do? We add a stability governor that's going to modify MPC reference command to maintain closed loop system in guaranteed region of attraction for the modified reference. And our reference governor, stability governor, looks like computational governor and looks like a reference governor. But the constraint it enforces here, it's a little bit different. It tries to maintain the state in the region of guaranteed region of attraction for unconstrained MPC, which is dependent on the current reference. So this pair of the state and reference command have to satisfy this condition. So this is basic idea. And what we see is that that's going to maintain stability for shorter horizon n and smaller terminal penalty lambda. Terminal penalty is something that also people don't like. And you get large region of attraction because with reference governors, you end up with a union of region of attractions for individual values of the reference. So that's not surprising. So that's the basic idea. You can work out the details. I'll skip it in the interest of the time. They're in the paper that we've published. But there is a way to generate implementation where everything is explicit, and we're able to show recursive feasibility, prove asymptotic stability, as well as finite time convergence of the modified reference to true reference. So there's usual theoretical guarantees that you would expect in this situation that we've been able to establish. Just to show a video, this is inverted pendulum on a cart. And here you see there is a red point which corresponds to a command for the cart position. And the blue point is the modified set point by the stability governor. And n is the horizon. So here I'm looking at the long horizon. And typically, the longest horizon, this region, unconstrained region of attraction, is going to, terminal unconstrained region of attraction is going to expand. But even with 85 steps, it's not enough. I'm starting outside of the region of attraction, and I'm losing stability. If I do stability-governed implementation, you could see I'm perfectly stable. In fact, I can reduce this horizon to 50. Of course, the motion is a bit slower. So that's basically what this does. All right. If I have time to briefly touch on the last topic, it looks like I get thumbs up, so I'll continue. And very briefly, want to talk about connections with multidisciplinary design optimization, or more specifically with something that we call control-aware design optimization, where the problem is a bit different. What we are trying to do is that we are trying to look at design, in particular design of vehicles like aircraft or supersonic aircraft in our specific case study that we've done. And what we realize is that when we optimize its design parameters, for example, the wing shape, we often optimize it for things like fuel burn, takeoff weight, range of the aircraft. But there is also important characteristics of this aircraft that have to do with its ability to perform maneuvers. For example, I want to be able to take off and land. I have to be able to follow the glide slope when I'm landing, and if I'm hit by disturbance, I should be able to still follow the glide slope within the prescribed limits. So that problem, because the maneuvers depend on control, is somehow coupling the design aspect and control aspects together. And so the question is that then can we somehow define a control agnostic approach, ideally, that ensures vehicle controllability, ability to perform these maneuvers in the system design phase. So simultaneously optimize parameters while guaranteeing that there is a control that is going to do the job. Turns out that such problems can be reduced to bi-level optimization, where you're trying to minimize a function of design parameters, for example, wing shape, subject to a constraint on the value function of an inner loop optimal control problem, where this inner loop optimal control problem gives you the cost of your maneuver, right? And if you use penalty function, if the maneuver doesn't exist, then this penalty function will be basically very large. So the setting, this is a bi-level optimization problem. So you're saying that you want to minimize a function f of pp as a design parameters. And then you have a constraint, j star here is the optimal value function of your control problem at a lower level. And s has to be less than equal than j bar. This is what we call this control-aware design optimization. So we have an MDO optimizer, multi-disciplinary design optimizer that adjusts parameters. And then we have a control optimizer that's going to worry about the maneuver here. Now, one interesting thing that we realize is that this bi-level optimization problem is not so dissimilar to what we have in model predictive control. And let me explain what happens in model predictive control. Let's look at this picture on the right here. We have a control optimizer that decides on a control sequence in MPC. That optimizer depends on the state, on the current state of your system, which is a parameter in this optimization problem. And this parameter evolves according to the plant dynamics, right? Now, what happens on the picture on your right, on my left, is that we have a parameter here as well. This is design parameter. And that parameter doesn't vary according to dynamics of my plan, but it varies according to dynamics of MDO optimizer. But otherwise, at this lower level, it's a very similar picture. So what does it suggest? Well, it suggests that some of the same tools that we use in control theory to analyze the picture on your left can be exploited for the problem in bi-level optimization and control-aware MDO. Notably, we can take advantage of small gain theorem and input-to-state stability to establish convergence guarantee of inexact bi-level optimization algorithms. So what basically this means that we don't have to wait for the control optimizer to converge while iterating on the design parameters. That's what basically this means. We can accept inexact solutions here. Now, can we make this precise? We've done a bit of work along these directions. In particular, if you look at the inner loop problem, being linear quadratic optimal control problem, this is in discrete time, which depends on this parameter p. And then under assumptions on the cost in the outer loop, we can look at bi-level proximal gradient algorithm, perhaps simplest algorithms of this kind. And we look at iterations in the parameter as well as in the control, and we can show that there exists a bound on the number of iterations in the inner loop, such that if you perform at least that number of iterations, this whole algorithm is going to be convergent to the solution. So we end up with a convergence guarantee. And the results, again, this convergence guarantees are obtained by using small gain theorem. Recently, we've been expanding this work, and in our inner loop, we now allow alternating direction method of multipliers, ADMM. And the nice thing about ADMM is that it allows us to handle also equality constraints in the inner loop, as well as it has a number of other properties. So we have a now complete theory for that. And in a more fundamental way, from the perspective of the outer loop optimization problem, what is it we are doing? Well, we are basically doing some kind of gradient descent where we are relying on inexactly computed gradients. We are relying on inexactly computed gradients, and then we are able to establish convergence guarantees to the solution in this setting. So that seems to be an interesting idea, how to apply small gain theorem in other settings of this kind. And there have been a number of papers that we started to write, in particular for Newton's method for generalized equations, inexactness in bi-level nonlinear optimization. We call it gradient-free, in the sense that it allows the use of inexact gradients, and even some problems in game theory. For computations in game theory, we can exploit these ideas. So that does bring me to my last slide with a few closing thoughts. I talk about computations and model predictive control, and it's clear that inexactness of computations in MPC is going to affect closed-loop dynamics and closed-loop properties. We can derive bounds on the number of iterations to ensure closed-loop stability with receding horizon model predictive control. I haven't talked about shrinking horizon MPC. In shrinking horizon MPC, your end time of your maneuver is fixed, and so the horizon shrinks every time you approach your end time. And it's of interest, for example, if you try to maybe do some kind of landing or waypoint following problem. And it turns out that you can also do similar analysis for the shrinking horizon MPC and get various bounds on the number of iterations that you need. Supervisory schemes for MPC can be developed that improve reliability of MPC with short horizon, reducing computational time and expanding the closed loop region of attraction. I think I spoke about at the end that analysis of inexactly solved bi-level optimization problems in MDO can benefit from control-theoretic tools such as small gain theorem. And finally, I should point out that much can be learned from treating application problems in different domains, and it's a rich source of challenges, but also ideas of various things that you can try that they can later, some of them can actually lead to some interesting theoretical developments. And I'll stop here.
Okay, now it works. We have time for questions. Paolo?
Thank you for the very nice, interesting presentation. So I was wondering, when you calculate L star, that is the minimum number of iterations that you need. I think I probably missed some details about the guarantees that you get and also the problem setting. Is persistent feasibility included in the guarantees that you get? Like,
so let's just say the current results. So the existence, there's two different types of results. The existence of L star can be established in a more general setting than specific bounds on L star. For the specific bounds of L star, we typically look at linear quadratic MPC with control constraints. That's the easiest case to analyze, in which case the issues of recursive feasibility, they're very easily satisfied because you only have control constraints. Then, as a next step, what you can do is that you can establish a region of attraction or a region such that if you start from that region, then all other guarantees, including recursive feasibility, will hold. So that's how the current state of the results. And I'll be very happy to show you, I have 3 slides to show actually how we estimate L star based on linear quadratic MPC.
and I think you said that, right? But the price you pay is that the region of attraction gets just smaller, right?
You know, this is a very interesting, the behavior of region of attraction with L star, it's a little bit non-intuitive. So in other words, it's almost like, at least in a linear quadratic MPC setting, if you look at analytical bounds, it's almost like this, that for some value of L, you don't have it, and then you have it.
Ah, okay.
So it's kind of like this. And this is, we've been looking at this problem, but some non-intuitive things happen, at least with the type of bounds that we are currently using. But yes, it's roughly speaking, what happens is that you need to have a contraction somewhere. And in a linear setting, linear models, quadratic cost setting, you know, things start to look more and more like linear, and so you either have something less than 1 or not. I think in nonlinear problems, you can have more interesting behaviors.
Right. Thank you.
Other questions? Well, I will make a question for which I already have an answer, but just to provoke you a little bit. But are we sure that with the technological increase of availability for what concerns computational power, it is relevant to look into reduction of the computational cost of MPC?
You know, I think it depends on applications that you consider. And as I said, you know, if you look at quadcopters at the moment, they are fairly computationally limited. And that question has to really be answered in strong connection between applications that one might have and computational hardware. I should also point out that the speed is one aspect of this whole area of research, how quickly you can compute the solutions. But the other one is reliability of computations, and that becomes important, especially when you deal with nonlinear MPC problems, because then, you know, you can have all the time in the world to compute, but if you converge to wrong solution, then that's also doesn't do you any good. But yes, I would say that as I see cases where there is there's definitely growing computing power. One thing that you have to also realize, that at least my experience in industry is that, yes, you know, the computing power grows, and you know, there has been Moore's law, right? Or I forgot what's the name of the law, but essentially the number of transistors doubles every 18 months or something like that. And what I've seen in industry is that sometimes, while this is true, you tend to keep the computational power about the same or grow slower, but then actually transfer some of these improvements into cost reduction. So basically get, like in automotive, you might want to get a lower cost module, which will be a bit more capable, but maybe not as capable as as you'd like to have. So at least at the moment, I see across a range of applications, computations being, in terms of speed, being an important limitation. What happens in the future, it's hard to say.
So if there are no other questions, are there other questions? Oh, Frank.
Thank you. Wonderful presentation, very interesting. I see, of course, that safety critical applications is a clear domain where you apply these kind of methods. I was wondering if you could let us know something about the application of these methods to nuclear systems. So, for instance, for the prediction of criticality, evolution, and how to control this. Thank you.
So this is very interesting. I'm not an expert on nuclear reactors, for example, control. I had interest in this type of problems from general application standpoint. And what I realized is that many reactors are made very safe by design. That is, the control task is made simple through the design. And so, and partly, this is just because of the technology involved. I don't know if things will change with some of the more modern, like a small modular reactors that people are considering. And I think there's a range of other possibilities where ensuring safety is absolutely critical. But I think the control, the reliance on control, at least at the moment, my sense is that it's not as heavy reliance on control, because really they are made safe by design, I think. That's my impression. But as I said, I haven't worked on these problems, but this is just my impression from talking to experts and
Thank you, Ilya, for the presentation. I just maybe missed the detail. I think it was with the battery of electric vehicles. I wonder, you said that you ensure reliability of the long-term prediction using what? Yeah, with the battery for the electric vehicles example.
Yes.
I think it was fairly at the beginning of the presentation. You said that you ensure the reliability of the long-term prediction using...
Yes, so the key question in its setting, the key question for us was, can you predict the vehicle speed sufficiently far ahead? And the reason is that the thermal dynamics are slow, and so you'd like to, for example, predict the vehicle speed 5 minutes ahead. And so initially we were skeptical, because the previous work we've done, for example, for hybrid electric vehicles, we could do it 10 seconds into the future, and that, if I remember the numbers correctly, it gave us between 1 to 2% improvement for HEV energy management. But tools since that time and ideas have advanced, and so we looked at queuing models for short. So this is in urban driving scenario where, for example, we drive through, let's just say, 5 intersections with traffic lights, and we are assuming that we have tons of historical data. What we're interested in doing, and in fact, near University of Michigan, we have so-called Plymouth Road that has a very notorious 5 traffic lights where there's a lot of traffic jams, and depending on time of day and day of the week, different things happen. So we have a lot of data for that. And so what we found is that by utilizing different techniques over different horizons, in particular queuing models, which are more kind of first principle based models for short horizon, and then using a neural network and then Bayesian network predictions, where we update. So for example, one thing we have found is that if you condition your prediction on whether the vehicle stopped at the first traffic light, then your accuracy increases quite dramatically. The other thing is that if you do it on spatial domain, that is as a function not of time but of distance, that improves things as well. So with a number of these observations and sort of using some of the tools with Bayesian networks, we've been able to get reasonably good accuracy for those applications where we can demonstrate energy efficiency improvements. I'd be very happy if you send me email. I'd be very happy to give links to papers where these developments were reported.
I would love to. Thank you.
So Bruno?
Thank you, Ilya, for the presentation. I tried to keep count of the publications that you had in the last couple of years, but I ran out of bits by half time, which is great.
It's not always good.
Well, good publications, not just publications. So, so you stressed a lot about the impact of the inexactness of computations, right, with regard on stability and other properties. Is there any work that relates the explicit MPC kind of results to stability, for instance, right? Which addresses also the question that Emanuele asked, right? When you don't have the computation, you might just, rely upon, storing the solution and then just having to retrieve it. Is there any relationship between stability results and the coarseness versus the fineness of this?
Yeah, there has been, definitely there has been work on trying to understand if you have an explicit solution and you have approximation errors, could this translate into instability? And I have to remember the references, but I know where to find them. So right, yeah, it's, well, anyway, I have my memory on recall is not great, but yes, this work has been done. Now, one thing that I should point out that certainly when we started looking at these ideas on automotive side, which is around 2000, it appeared that explicit MPC was the way to go because you don't have, I mean, it's easier to certify, you know exactly what the computation time. But what transpires is that when you store, your computer store the solution, the solution can be quite complex. And even in linear quadratic MPC setting, you have a lot of these polyhedral regions as well as gains. And so the time to go through these regions and just to find the right one for higher order systems, maybe with 4 or 5 states already, can exceed the time to perform a few iterations of online optimization. Now, people have done various approximation schemes, how you can eliminate some of the regions. For nonlinear MPC, there has been work approximating such solutions with neural networks and with some kind of nonlinear approximators. But my sense is that you're fundamentally against the curse of dimensionality limit, that you're storing multi-dimensional function, and that's difficult for high-dimensional problems. Now, if the problem has 2 or 3 states, maybe not many constraints, then I think that's quite feasible.
Yeah, and I would say if the gradients are not too high, maybe you can compact.
Exactly.
Yeah.
Exactly. But how to do it systematically in high dimensions? That still is a challenge. I mean, other ideas people, for example, have tried to take advantage of symmetry of the problem. For example, about different axes, and you could kind of generate solutions about 3 different axes, and then that gives you total control law. I think always new ideas can be found, but I at some point convinced myself that you are kind of against this curse of dimensionality type of a limit to develop a nonlinear kind of nice, easily parameterizable nonlinear approximation. Again, things are evolving and nothing remains cast in stone. If there is a deep neural network that somehow does everything, then that's a different world. So.
I also had a follow-up question concerning, you mentioned before, Bayesian network predictions, was it, if I'm correct? Actually, what is it more precisely, and how does it work?
Well, so the idea is that you essentially define conditional probabilities that, of your prediction. If something happened in the past, what's the probability of what's going to happen in the future? And so you build sort of a sequence of events. For example, am I stuck at my first traffic light, right? Am I stuck at my second traffic light? Am I stuck on a third traffic light? And then if I have historical data, I could estimate the probabilities of getting stuck and probabilities of what's going to happen. So it goes back to ultimately to Bayesian inference and Bayesian rule for basically a posteriori probability estimates.
And what now if you don't have enough historical data? Do you kind of try to construct kind of like to make a prediction, like how you can you compensate if you don't have historical data for like situation you didn't expect?
Well, so very good question. You know, I can only give a generic answer because I think a lot of things we've done are really heavily tailored for historical data. And in a vehicle driving context, you can instrument traffic lights and see cars passing by, and you can kind of collect those data. You know, generally probabilities, you could interpret them also as reflecting of your beliefs. And if you have reasonable beliefs, you can still configure those models just based on somehow intuition. But I think it's much harder to do. So.
Okay, so I imagine there are other questions, but at a certain point I have the task to close it here. I'd like to say a last thing, that is reporting a private conversation between me and Ilya, if Ilya allows me, but he doesn't know what I'm going to say. So that is so. 2 years ago, when Ilya was here with us for a month as a charge remote, when he went back home, I remember that we had a call and he said, you know what, when I left Brussels and I arrived here, I felt like I left a familiar place and I would be very happy to come back again. I hope that he will say again something like this in a few days when he will be back home and that we can have him again as a guest here.
Absolutely, I predict that will be the case. And again, thank you so much for organizing the program. It was a real pleasure to be here.
Thank you to you, Ilya. So a last round of applause.